Hi everyone, so this is the term 1 week 2 physics AMS quiz. So here we have the first question, which says, which of the following statements describes the safety measures while using radioactive material are true? So eating is allowed while handling radioactive sources. This is definitely false because you can't eat. You can't even touch the radioactive source, so how are you gonna eat? So make sure the radioactive source is pointing away from you. This is right because you don't want it affecting you in any way, so it doesn't have to be pointing towards you. Radioactive sources should be locked up in a safe place, like a lead box. This is true because, like I said up, you do not want the radiations affecting you in any way. It is safe to move a radioactive source with your hands. It's definitely not safe. Radioactive sources should be identified by your eyes only. No, you should also do some other types of tests because your eyes aren't enough to identify it. Next question. Underline the factors that's affecting the rate of radioactive decay. So, does the position and where the radioactive decay is happening matter? No, it doesn't. Does the temperature matter? No, it does not. Does the nature of the radioactive decay matter? Yes, it actually does affect the rate. Does the quantity? Definitely, the quantity does affect the rate. Does the pressure all the radioactive decay is under effect? No, it does not affect. Okay, so for this question, it says a radioactive source emits radiation into a space where a downward electric field is present. This source emits a beta particle and a gamma radiation. 3 detectors A, B, and C are used to detect the radiation. So detector A will detect. A is positive. A is going towards the positive side. Beta particles are negative, so positive and negative they attract. So detector A will detect the beta particles. Detector B means whatever radiation is passing through will remain going straight without getting affected by any of these magnetic fields, which can only mean it's gamma radiation. And C, it won't detect anything because there is no alpha radiations here. So for this question, you just have to memorize how each track looks like. So alpha is always straight and bold, beta is always zigzag and less bold, and gamma always looks like scribbles. So for this question, it's the exact same as the last question we did. Just put the same answers. Now for this question, where might the background radiation come from? Does it come from cosmic rays? Yes, it does. Blocks of lead? It does not, because lead is the main factor that can weaken or stop most radiation, so definitely not. Several pieces of thick aluminum? No, it doesn't. Radon gas? Yes, it does come from there. And food and drink. And like, if you want to know where you got the answer for this, you come back here. Radon, cosmic, and consumer product is what you'd consider food and drink. So detected radiation rate equals total radiation rate minus the average background rate. Select the expression that should be multiplied by the detected rate to get the total radiation emitted from a source. A is the detected area to the radiation, and R is the distance between the detector and the source. So for this question, just memorize its formula. It's 4 pi r squared over A. And for anybody who doesn't know, it's 4 pi r squared because that's the formula for finding the area of a sphere divided by the area of the detector. So yeah. Okay, for this question, it says the actual radiation rate from a source S is 27 becquerels. The radiation counter detects a radiation rate of 73 becquerels when placed near S. What's the background radiation rate? As we saw in question 7, background radiation rate equals total radiation rate, which is 73, because this was after you brought the source, 73 becquerels, minus the actual radiation that came from said source, which is 27. So once you actually calculate these, you're gonna probably get the answer on your calculator, which is 46 becquerels. Now on to the next, unstable. So C, it's 12 over 6. So for this question, what we have to do is we have to find out how many protons and how many neutrons is in each question and find the ratio between them. So for this question, you do 12 minus 6. You find out that you have 6 neutrons. We always know that the down number is the number of protons. So the bottom number is the number of protons. To find neutrons, you do the top number minus the bottom number. So neutrons is 6 and protons is also 6. So 6 divided by 6, you're gonna get that the ratio is equal to 1. And there's a rule that states that if your ratio is over or equal or like just over 1.5, your element is unstable. So now here you have 2 protons and 6 electrons. So 6 divided 2, you're gonna get 3. So here this one is unstable, so you select it. Here you do 232 minus 90 on your calculator. You're gonna get 142. So you have 142 neutrons divided by 90 protons. You're gonna get it's equal to 1.5777 and so on. So it's more than 1.5. So you have to choose it as unstable. For this one, it is 30 neutrons and 26 protons. So once you put that in your calculator, you're gonna get the answer of, you're gonna get 1.15, which is less than 1.5, so it is not unstable. Okay, so now for this last part, 80. Once you subtract 210 from 85, you're gonna get that you have 125 neutrons. So now you need to divide that by 85. You're gonna get 1.47 something. So you round it up. 7 is bigger than 5, so you could round it up and it will be 1.5 exactly, making it also unstable. Now moving on to, okay, so the answers are this one, and this one. And now moving on to the next question. "16 grams of radioactive material are isolated. After 15 hours, the mass of the radioactive material is measured to be 8 grams. After an additional period of 30 hours, the mass is found to be 2 grams. The half-life of the radioactive material is..." So the half-life is the point where the 16 grams becomes the half, which is 8. Here, it's really easy. They immediately told you that your half-life is 15 hours. So it's measured like after 15 hours, it becomes 8. So that's just like the half-life you're gonna use. So your answer is just 15 hours, which is 15. Next question. What type of particle does the radiation source give? Okay. A radioactive source emits radiation into the space where electric fields maintain 2 oppositely charged plates, like it's shown here. What type of particles does the radiation source give out? So it gives out mostly A because that's the most. A is going towards the negative side. So positive and negative attract. So positive is alpha particles. Now for part B, which material of the shield will ensure a narrow beam of radiation regardless of the nature? It's lead. Lead is thick enough to stop all the radiations and to really decrease gamma radiations, but never stop gamma radiations. Okay, so for this question, the tracks in the cloud chamber are left by it's a condensed liquid. This one, just memorize it. The radiation that leads to the creation of such tracks are most likely a gamma, because look, if it looks weird and it's not going in any specific direction, way, or line, or any zigzag, it's gamma. So which of the following is true about the presence and the direction of these magnetic fields in the cloud chambers? So this one here, it's impossible to tell because you can't see any specific direction where it's going. And this one specifically, it's not affected by any magnetic field, so you can't tell if it's going up or down. Okay, so this question, it tells you that a radium source emits 3 types of radiation in the presence of magnetic field. The tracks are formed in a cloud chamber by these radiations shown below. So you could see that here you have one that's going down in a clockwise direction, one going straight, and one going up. So track 1 is formed by beta, because always beta is moving or curving. Track 2 formed by an alpha, because it's going up. And track 3 is formed by a gamma, because it remains undeviated while passing through. Now the direction is into the plane of the picture. Now why is it into the plane? It's because the beta is moving clockwise. If you see beta moving counterclockwise, then it's going out of the plane of the picture. Okay, so now last question. So for this question, it's telling you that the GM tube detects background radiations of 750 counts in 5 minutes. The background radiation is detected so becquerels is counts per second. So here we have 750 counts, but here it's in 5 minutes, so we need to convert this to seconds. So 5 minutes times 60 seconds in a minute will give you 300 seconds. So you have 300 seconds here and 750 counts. So you need to divide 750 by the 300, and once you divide them on your calculator, you're gonna get that the background radiation is 2.5 becquerels. And the major source for background radiation indoors is radon decay. Like this one, just if you look at the pie chart given in your book, it's gonna say that radon has the highest. So yeah, here it's 2.5, and here it's radon. And with that, we're done the quiz.